So here is in a nutshell for 1.2 part B, memory and storage. So I'm going to go through converting back and forth from positive denary whole numbers to binary. So let's do that first. So I'll do it the quickish but full explanation. So our number system, denary or decimal, whatever you want to call it, has 10 digits 0 to 9. Okay? So when we have a number like 367, I hope you know that essentially what you're doing is multiplying the top number by the bottom to get 60 there, to get 7 there, and you're adding them together to get the number 367. Okay, so that's how you do it in our number system. Now these, every time it goes here, it is times 10. And it is times 10 because we have 10 digits. Okay, so that's why it's times 10. So if we apply the same principle to binary, I'll just do 4 bits. You've got 1, 2, 4, 8. Now every time it goes to the left, it doubles because binary is a 2-digit system. It only has 0 and 1. Okay, that's a 0. So yeah, so that's what it is. So if I put, and you only have 0 or 1, so let's do 1, 0, 1, 0. So you multiply the top by the bottom. 8 times 1 is 8. 4 times 0 is 0. 2 times 1 is 2. 1 times 0 is 0. And you add them together to get 10. Now, because it's binary, do you really need to multiply them by 1? Probably not. All you really need to do is just add all the numbers that have a 1 underneath, and that's how you get the decimal or denary version. So binary is actually quite easy, especially to get the answer back. Possibly slightly harder to go towards it, but so I'm going to do a more challenging number and run out of room. But fortunately for me, I'm on a computer, so I can adjust. And then last but not least, 128. So this is a full 8-bit. You won't get any higher than this in the exam. So it might say to you, write the binary out for, I don't know, let's do 103. A tough one. Well, I mean, it depends if you can do maths. So basically 103, first of all, what you do is you find the largest number that goes into it. So it can't have 128 into it because that's bigger than that. So that's 0. Okay, 64 does go into it, so put a 1 there. Now we need to find out how much we've got left. So we take 64 off. So let's do it this way. 3 minus 4 is 9 and 1 extra. 0 minus 7 is 3 with 1 extra. 1 minus 1 is 0. So we're left with 39 here, and we need to carry on. So repeat the same process. So now I've only got 39. Let's go move that up. So 39, right, you find the biggest number that goes into it. Well, 32 goes into it. So 1, then we take off 32, leaving us with 7. 16, no, that's too big. 8, that's bigger than 7. 4, that's not. Right, 7 minus 4 is 3. 3 is bigger than 2. 3 minus 2 is 1, and then we're left with a 1. And afterwards you can do this. 64 plus 32 is 96, 100, 102, 103. So you can check this after, but basically that's the way to do it. It's just a little bit of basic maths. So that's converting back and forth from denary. Now we've got a little bit more of a complicated topic, so I'm going to take this a bit slower. We've got the topic of how to add 2 binary numbers together, right? So it doesn't actually matter what they're worth. So I'm not even going to write the values along the top. Actually, I will, sorry, because then we can check it after. I lied. Let's do it a bit neater this time, though. But I mean, it doesn't, when you're actually adding it up, it doesn't matter if you know what the numbers are, as long as you get the right answer at the end. But I suppose it's better to check it if you look at that. Right. So let's add 2 numbers together, relatively easy ones. Let's just add. Actually, let's just do a random. Oh, I don't do that because it'll be harder to check after. Right. So this is what you do. Now, I always write out the table first, because when you're adding two numbers together like this, there are only four possibilities. Because you've got a carry, okay? You can't have a carry on the first number, but there is a possibility that you can carry over onto the next line. So there are four possibilities: that the row adds up to 0, the row adds up to 1, the row adds up to 2, or the row adds up to 3. So what I do is I write 0, 1, 2, 3, because they're the only options I can get when I add up the row, because I could have a carry here from the previous row. I won't, but I could. So actually I will. So no, I won't. Anyway, but the point is I could. So I write out 0, 1, 2, 3. Then I put carry and a result. So then I write the binary for each of these numbers in 2 digits. So the binary for 0 is 0, 0. The binary for 1 is 0, 1. The binary for 2 is 1, 0. And the binary for 3 is 1, 1. So now what I've got is a little table that's going to help me work it out. So I go, right, I add up. 0 plus 1 is 1. So I write 1 in binary. So I put 0 there and 1 there. That's my carry. Now I add that up. 1 plus 1 plus 0 is 2. So as you can see here, 2 is 1, 0. So I write the 1 here and the 0 here. 1 plus 1 is 2. So I write 1 here, 0 here. 0 plus 0 plus 1 is 1. So I write 0 here and 1 here. And all I do is just do this table all the way along. It's actually really easy. 0 plus 1 plus 0 is 1 still. So that's 1 here, 0 here. Again, 1 here, 0 here. 1 here, 0 here. Okay? So now I'm left with, obviously 0, 0, 0 is 1. If, by the way, you ever get a carry on this number, so let's say this ended up with a 3, which would be 1, 1. I'll do that example in a second. If anything ever goes over the end of this, it's lost. And this is called an overflow. And the computer knows it's happened, but essentially it knows that, it's gone too big for the memory. So let's just check these numbers. I didn't even look what I was doing. So 32 plus 4 plus 2 is 38. So this is 38. Okay, just double check that. 32, 36, 38. This is 64 plus 16 is 80, 83. Okay, so this number is 83. So we should, hopefully you'll know that this is, add 40 minus 2, 121. So this, it should be 121. Okay, but let's just check it. So we've got 64 plus 32 plus 16 plus 8 plus 1, because they're the ones that have got the ones below them. So 64 plus 32 is 96, 112, 120, 121. There you go. So that is correct. So I've done the math there. Okay, so let's try it again with two different numbers. We'll go through that again. So there we go. So let's do 1, 1, 1, 1. I'm not going to do loads. I'm just going to do like that. And then I'm going to do, actually, let's do 1. Hopefully that gets an overflow. Let's do that. And then you can see an overflow in action. Well, look, we're going to get lots of overflows. So right, here we go. So 1 plus 1 is 2. So 2 is 1, 0. So I'm going to do it in red. Actually, I'm going to write my I'll write my answer in red. So I'm going to put my carry there, 1, and right down here I'm going to write 0. Okay, because 2 is 1, 0. 1 plus 1 plus 1 is 3. 3 is 1, 1. So I write 1, 1. Okay, 1 plus 1 plus 1 is 3. So I write 1, 1. I always write this, even if it's a 0, just to get in the habit. So 1 plus 0 plus 1 is 2, which is 1, 0. So I write 1, 0. 0, 0, 1 is 1, and 1 is 0, 1. Okay, that's going to be the same again. 0, 1. And that's going to be 2, which is 1, 0. And that's going to be 2, which is 1, 0. You see, so here we've gone over the top, and this is called an overflow. Okay, so let's quickly do the math to check ourselves, because you can do that. 64 plus 8 is 72. 76, 78, 79. This is 79. 128 plus 64 is 192. Plus 32 is 194. 224. 224, 228, 230, 231. Oh, And another thing I can do, just double check that, is I can actually count the zeros backwards, because the maximum number is 255. Okay, so 255, if they were all ones, it'd be 255. So I know this is 24, so this number should be 24 because these are the zeros. I'm taking 24. If I put those to 1 and 1, this is 255. So if I take 16 and 8 off, I can actually double check that's 231. So let's add those together. Obviously, we're gonna get an overflow, so we're going to have to presume this is 256 for a second. Obviously, it's not actually going to be there. But yeah, so the point is we add them together and we're going to add 80, add 9, that's 240 is 3, 10. Am I being dumb? No, 310. Right, so let's just check that. So that would be 256, but of course that doesn't count, but we have to add it. Plus 32, plus 16, plus 4, plus 2, plus 32, plus 16, plus 4, plus 2, equals 256 plus 32 is 288, 298, 304, 308, and 310. There we go. So I checked it. So that's how you do binary addition. You will never get more than 2 numbers in a row like this. And if you ever did get a third number, just add the 2 and then add the result to a third number, which is what the computer does anyway. Right, so that's binary addition. Okay, right, so what's the next one on our thing over here? So we've done that. Let's actually lower this now. So we've done those 2. Let's just highlight the bit we're doing. How to convert positive D numbers into 2-digit hex and vice versa. Right, so hexadecimal. Hexa means 6, decimal means 10. So hopefully you've understood that hexadecimal is a 16-digit system. Now it does 0 to 9, exactly the same as our system. But then you've got an A, B, C, D, E, and F. And they represent 10, 11, 12, 13, 14, and 15. Not the greatest 3 there. Now, a lot of students struggle with hexadecimal, but I actually personally think it's quite easy. But obviously, I know the answers. But I think I think it's because students overcomplicate it. So essentially what you've got to remember is it has the same pattern as all number systems, okay? So the right digit is worth 1 and the next digit to the left is always worth the number of digits times it. In hexadecimal, you're never going to get more than 2 digits. So all you've got to remember is that this column is worth 16 and this one is worth 1. That is the worst line ever. So I'm going to redraw that with an actual line. There we go. So what you got to understand, so let's stick a number in. Let's stick A and the number 4. Okay, so 16 times A is actually 10, so this would be 16 times 10, so that's 160, plus 1 times 4 is 4, add them together, and A4 is equal to 164. The hardest bit is just remembering this, but actually when you think about it, once you get to 9, you can only just think, it's got letters, it's going to start with A, like, you know, and you know there's 16 digits, and so as there's 16, you know it's going to end at 15, because like we've got a 10-digit system, but we end at 9. Binary's got a 2-digit system, but it ends at 1. So just a bit of logic, really, just a bit of basic thinking, and you should be able to work the hexadecimal out. It stands for hexadecimal, and really you can kind of work it out on the spot. So let's do another couple of numbers just for the point of it. Let's do 7F. So 7 is just 7. So that's 7 times 16, which is 70 plus 35 plus 42. So that's 112 plus F, that's 15. So that equals to 127, if my math is correct. Let me just double check that. 632. 6 is 36. Yep, plus 6. Yep, that's right. Yep, so that's 127, 7F. Obviously, get the maths right. Double check in the exam. These are easy marks to fail. Okay, you don't want to fail these masks. So there you go. So 115, you add them together, and this one's worth 16 times. Really easy. It's actually one of the easiest ones, I think. Now, the only one that can be annoying is if they give you a number and you've got to convert it to this. So let's say they give you 180. Right, then you just got to think. Now, you could write out the 16 times table and then see which number matches up. Now, obviously, I know that 160 would be A here. Okay, because it would be 10. So I know that when I get 10 16s is 160. So you've got to think, how many will go into there completely? Well, obviously it's 11. because 11 times 16 is going to be 176, okay? And 11 is B. So I know that if I need to go back that way, that there's going to be B numbers of 16s, because 16 times 11 is 176. I'm left with 4, so this will obviously need to be a 4. So B4 is 180. Okay, that is a bit tricky. They normally give us something like 72 or something. And so then you might want to write out the 16 times table. 32, 48, 64. And then you must realise at this point that, you can't add 16 onto that. So you would then work out that if they gave you 72, let me just scrub out these, that you've got 72, so you've got 4 there. So this is going to be 4, and we've got 64. Now to get from 64 to 72, I need 8. So 4, 8. And let's just do it. 40 plus 4 times 6 is 24, so that's 64. Plus 8 is 72. So there you go. That is the way they would do it. It'll probably be a low number of 16s, because they don't want to test you up to, like, I don't know, they'll give you like 206 or something like that. But if they do, then just start from 160. You know that 160 is 10. You should know that 80 is 5, and you can work up from that number onwards to find the number that you need. So that is converting back and forth from hexadecimal. Now, one you often get, which is easier, which is really easy, is over here. I'll move this down. Is how to convert binary integers to their hexadecimal equivalents. So basically, you've got to convert between binary and hexadecimal, which actually is easier. It sounds difficult, but it's not, right? So what they'll do is they'll give you, they'll either give you two. Let's do from hexadecimal to binary. So hex to binary, right? So let's say they give you F4 and then say write that in binary. Well, what you do is you write it as in 2 halves. It ends up being one number, but you think of it as 2 halves. So let's write 4 in binary with 4 digits, because the whole thing about hexadecimal is, what's good about it is that 2 hexadecimal digits is a byte. Each digit is 4 bits. Okay, so if you think about it, what is 4 in binary? So let's do that in 4 bits. 1, 2, 4, 8. So the binary for 4 with 4 digits is 0, 1, 0, 0. And what is F? F is equal to 15. Okay, write the table out. So once again on the left hand side we do this. So 15 is all of them. I know that because it's the biggest number you can do with hexadecimal. And so that would be how you convert it from to F4. It just ends up being 1, 1, 1, 1, 0, 1, 0, 0. Do it as 2 chunks. If you really wanted to, you could convert that. 15 times 16 is 240 plus the 4. So F4 is 244. In case I did the math really quickly there, but I just did 16 times 15, which sounds difficult, but remember it's just 160 plus 80. So that is 240. And then you add the 4, because that's only worth 1. There you go. So you could just do 240 and then use your normal binary skills, but that'd go 1, 2, 4, 8, 16, 32, so on and so forth, if that was going to be done that way. It's only when you do the digits individually that you do it this way, like this, where you do 1, 2, 4, 8, 1, 2, 4, 8. Obviously, if you're doing the digit, you actually went straight to 2, 2, 4, 4, you do 1, 2, 4, 8, 16, 32, 64. Okay, so that's how you do that one. I'll do one more just for the sake of it. So let's say they give you 7A. Okay, so A is 10. So remember 1, 2, 4, 8. To do 10, obviously it's 1, 0, 1, 0. And then to do 7, 1, 2, 4, 8 is just 1, 1, 1, 0, like that. And then that's the answer, really. There you go. Simple as that. Not that difficult if you can remember the system of just doing each digit individually and putting them together. And if you're wondering why this is 1, 2, 4, 8 and not bigger numbers, you're like, what? Doesn't make any sense. Just remember that this number is actually worth 16. And this is only worth 1. So these are worth 1, but these are actually worth 16. And if you were to carry on, this would be 16, 32, 64, and then 128. Okay, so these numbers are worth 16 times these ones here. Yeah, 8 times 16 is 128. 8 times 4 is 64. 8 times 2 is 32. 16 times 2 is 32. 16 times 4 is 64. 16 times 8 is 128. So we write 1, 2, 4, 8. Just remember though, when we were doing they're actually worth more, but because we do that after. So that's if you're confused as to why it's like that. So there you go. That's the 2. Now the annoying one is, I suppose it's not that annoying. Binary to hexadecimal, not that much different. So let's just pick any old number. Okay, so you break it in half. 1, 2, 4, 8. I'm not going to write it every time. So this is 8. This is 4. That's 12. 12 is C. Okay, because A is 10, B is 11, C is 12. This is 8 plus 2 plus 1. This is 11. So 11 is B. So you just write B, C. So that would be, it doesn't even matter what this is. They're not asking you to convert this to a number, you know, whatever this is going to be. It would be 176 plus 188, I think, but I'll have to double check that. But it doesn't matter because they didn't ask you to convert it to decimal. They asked converted it to binary. So hexadecimal to binary or binary to hexadecimal is actually not ridiculously difficult. You just got to know that you break it in half. But there you go. So this is the last one. I'm not going to have this in the mock exam for December, but just so this video is complete for any other time. Binary shifts. So easy. I'm going to explain it now. So basically, in a binary shift, what you do is you shift the digits down a certain direction. So let's do this. If it was a binary shift, right by 2, then you're moving all of the digits 2 to the right. So if you imagine this is the dead zone, everything that goes off the end is dead. So you're basically moving all of your digits 2 to the right. So we would write, you know, so these move 2 to the right. So you start here 1, 0, because that's these 2 that are dead. But we write them anyway, because it will help me to know I've written them right. 0. So I'm writing it this way. 1, 0, 0, 1, 1, 1, 1, 0. 1, 0, 0, 1, 1, 1, 1, 0. So these have all got, now these fill up with zeros. You always fill the gaps with zeros. And so what's happened here, you've shifted it to the right by 2. What actually happens, every time you shift it to the right, you're dividing by 2. So if you shift to the right, if you're shifting right by 1, it's divided by 2. Now, a lot of kids then go, oh, right by 2 will be divided by 3. No, it's actually divided by 4. It doubles every time like this. So every time you shift them to the right, you're halving it. But you're halving it and then halving it again and then halving it again. So you got to understand it's not, you know, you don't add 1 to the halving, you're halving it every time. And let's just actually look at what that is. And the same with the left, but left you'd be like doubling it. So let's just do a shift on, say, like, let's actually do left, but we'll just do it on 4 small digits because it's easier to understand. So we'll do 1, 2, 4, and 8. Okay. So let's do right first of all. Okay. If I shift it to the right by 1, I get this. Oh, no, I don't. I get that. I get the one over here that's gone, but it's gone. It's dead. Okay. If I shift it 2 to the right, I get this. And then I've got 1, 0, my dead ones over here that don't matter. So let's just delete those because, you know, you've got that they don't matter now. So they're gone. And you fill up any gaps with 0. Same as if you go left. We'll do left in a minute, but you fill up any gaps with 0. So let's add this up. So this is 12. This is 6. This is 3. So here, this has been shifted right by 1. Okay, and so divided by 2. This has been shifted right by 2. And we've divided by 4. A lot of students don't get that. They think it's divided by 2, divided by 3. It's binary, so everything's going to be a power of 2. So let's show the opposite where we get bigger. So basically, a good exam question, but I'll go through it later, might be, explain the effects of a binary shift 2 to the right. And you would say something like, a binary shift 2 to the right would divide the number by 8. However, and I'm going to show you the however now, but I will do this question in the questions bit. What happens if we have this number? Right, so this is 7. So if we move it right to the right one, we're dividing by 2. So we should get 3.5. But the problem is we're going to lose our little bit here. And that actually equals 3. So what happens is if you're shifting to the right, and anything goes over the end, you lose accuracy. And the same can happen with the left. You can get an overflow. But basically, it can lose accuracy because it's like an integer division, but it always rounds down. So I'm just going to very quickly do the left because it's not much different. So if you do left 2, you would lose this one, which is a shame. because this is going to there. This is going to there, even definitely more out. So then this would go to here, and you would end up with 1. The actual answer would end up being 1, 0, because we've got the 0, 1, 0 off the end, and then 0, 0. So here it's gone up. It doubles every time it goes here, times 2, times 4, times 8, every time you move up 1. But once again, I've gone over the end, so this would be an overflow, and the data would be inaccurate again. But they nearly always ask you to the right for some reason. I don't know why, but they nearly always say, explain what happens if you move it to the right. Okay, so have a look at the questions, and you can see what to do.